a material has a Tg. In fact, my PhD thesis, one of my chapters was to do thermodynamics of glasses. So, I tried to calculate what should be the glass transition temperature for pure metals, and when I calculated for some of them, it turns out to be negative in terms of absolute temperature, something like minus 200 Kelvin. If that is the case, then in principle that particular metal, by some way, if I can bring it to absolute 0 before it actually crystallizes. See, all this is assuming that the liquid is not crystallizing. If liquid crystallizes during this cooling, then it is not glass. We are talking of if you can retain it as a supercooled liquid at absolute 0, then it would have that. The question then is, how do I measure that? So, that is why enthalpy also, we say enthalpy is 0 at 298, we are simply, because we do not know what is the base I should start with. So, I assume something. So, that is why all these standard states have come into picture. Okay, we start. Yeah, in the last class we have started talking about two component systems, and we started plotting what are called GX diagrams, and we talked about a simple model called regular solution model, and also a much simpler model called ideal solution model, in which the delta, the G of any phase, let us call it as an alpha, G alpha. I mean, where you put this alpha as a subscript or a superscript depends on you. Stick to something. Many people we usually use here, because this is the subscript is used for the component. For example, Ga, Gb, when I say, for example, as you go along you will know, maybe today's class itself, when I many times have to write Ga alpha and Gb alpha. We will see what does it mean as we go along. So, here for example, we know that this is Ga, Xa Ga plus Xb Gb plus delta G mixing. This is what we have written yesterday, and we said this delta G mixing is actually a composed of delta H mixing and minus T delta S mixing, and as a result, for an ideal solution we have written this expression as G alpha is equal to Xa Ga plus Xb Gb plus RT Xa ln Xa plus Xb ln Xb. This is what is for an ideal solution, and we said the moment it is not ideal, non-ideal solution, the one of the simplistic model, because all this whenever I am talking of a free energy of a solid solution, I need to start thinking about how the A and B atoms are interacting, and then give a model to it, and then do some measurements. How do I do measurements in terms of if I want to measure for this, how do I measure it? Is there any way? Yes, if you do DSC, if let us say you take A and B metals, you mix them and then do a DSC, if there is a positive interaction or a negative interaction, you would see it in terms of what is called heat of formation. This heat of formation we use calorimetry, and more sophisticated thing is a DSC, differential scanning calorimetry, and if you use DSC, in principle one can do. So, there are large number of people who have been measuring this delta H mixing, and from that we can come to know whether they are intermetallic compound forming or whether there is a repulsion between them, because of which there is a delta H being positive, and from that you try to fit from the measurements to the model and say yes, my model of regular solution or subregular solution, things like that are working. So, in a regular solution model, we assume delta H mixing as omega into XA XB, where omega is what is called interaction parameter. So, I can now basically put this in this, and then simply I will not rewrite this whole thing, I will simply say plus omega XA XB, this whole term plus omega XA XB, that would become the free energy of a solid solution if at all it is following a regular solution model. And this boils down to this equation when omega is 0. When omega is 0, that means interaction between A and B is 0, and that is what causes what is called an isomorphous solid solution. So, you will see as we go along when we go to the phase diagrams. And whenever you see the omega being positive, we say there is a repulsion. A and B do not want to mix into each other, and that is what causes what is called miscibility gaps in phase diagrams. And these miscibility gaps slowly lead to what are called the eutectics, peritectics, even to the extent of monotectics. We will see in possibly the next class what is called evolution of phase diagrams. How do phase diagrams evolve just based on thermodynamics? We will see that. Till then, have some patience. So, if this is negative, if omega is negative, that means there is an attraction between A and B. Any attraction always causes the formation of compounds. And here also, depending on how strong is the attraction, you have compounds with different melting points. Some of the compounds may have very low melting point, and some of the compounds may have very high melting points. If you look at some phase diagrams, you see the two pure metals have very low melting points, but the compound has extremely high melting point. So, that is because the two elements have such a strong attraction that this compound, the bonds in the compound cannot be broken easily. Melting point is basically an indication of bond breaking, and that is why you can easily correlate the melting point of a metal to the bond strength of that within that particular metal. So, you can see, so omega negative means attraction, that means formation of compounds. Omega positive means repulsion. Repulsion means what is called immiscibility, or I can call it as miscibility gaps, which finally ends up into phase separation. Now, people have seen, as possibly we have touched upon in the last class, that this cannot be always true. What I have done in this is, I have assumed that the interaction parameter is the same throughout the phase diagram. From one end of the phase diagram to the other end of the phase diagram, I assumed it to be the same, which is actually not always true. When I simply look at a number of phase diagrams, I see the solubility of one element in the other is different from two ends. We took the example possibly in the last class on copper zinc. Zinc dissolves in copper very much, whereas copper does not dissolve in zinc, and we tried to give a logic for it based on the valency. And if that is the true, then the interaction between A and B atoms is different on one end of the phase diagram, and it is different on the other end of the phase diagram. And this has brought in what is called subregular solution model. Where people say that the delta H mixing, I mix up once in a while, delta H mixing is omega XA XB into XA omega A plus XB omega B. That means, now we are talking of two interaction parameters, one on the A side, one on the B side. that means the interaction between A and B atoms on the A side and the interaction between A and B atoms on the B side, and which could be different. The moment both of them become equal, then what should happen to this equation? It will become same as regular solution, because assume that omega A equal to omega B. If omega A equal to omega B, this comes out of the equation, and then what you will end up is xa plus xb, and xa plus xb is 1. So this equation will become same as this equation. So that is how we can visualize this, and this is a kind of a next level of non ideality. And then people observed that this is also not really fitting in very well. Why? For example, if you look at a phase diagram such as magnesium silicon phase diagram, how many of you have seen magnesium silicon phase diagram? Anybody who knows how does it look like? Mg2Si is a very important compound in aluminum alloys. No. Okay. If you remember, if you have not seen it, okay, I will not bother about the actual temperatures much, but give you a schematic. Okay, obviously this should be silicon side, this should be magnesium side, and do not bother about this at the center of the phase diagram, but this is actually Mg2Si. So that means this is on the magnesium side. So you see a phase diagram like this, it has two eutectics and one compound. So that means suddenly at the composition of Mg2Si, when two atoms of magnesium come together with one atom of silicon, suddenly there is a strong attractive interaction between the two, and everywhere else no. For example, on the silicon side, magnesium does not dissolve in silicon, that means delta H is positive. If it is negative, it would have dissolved, there should have been solubility. And similarly on the magnesium side also, silicon does not dissolve into magnesium, there is almost negligible solubility on both the sides if you carefully observe the phase diagram, but suddenly at this position there is an attraction and its melting point is higher than that of both the pure metals. This means that the interaction at certain compositions suddenly becomes attractive. For example, there are many intermetallic compounds. Our famous one that we know in steels is Fe3C. So that means when you bring 3 atoms of iron and 1 atom of carbon together, and there is a strong attraction, but if you have 2 atoms of iron and 1 atom of carbon, there may not be. So this is based on variety of factors. People have classified them into variety types of compounds, electron compounds, size factor compounds. Let us not go into details of them, but there is a possibility that the interactions can be specific to certain specific compositions. And if I come to either this side or this side of Mg2Si composition, that interaction vanishes. That means the free energy of that is strongly negative at this composition, and this is the reason why people had to use some other models beyond the subregular, because subregular cannot account for this. Simply if you assume that there is some interaction on the A side, some interaction on the B side, and then simply try to find out the delta H mixing as a function of that, you cannot actually predict that there is a compound in the center. So people have brought in what are called cluster models, cluster variation models. We will not go deeper into this, just to give you a flavor. If you are interested, come to me, we will talk more. Lot of people, all this, so they assume that there are a lot of clusters inside a material, and these clusters have depending on what is the stoichiometry of the cluster, you have certain free energy or certain interaction, certain interaction parameter, and based on those clusters try to find out which cluster has the lowest, and then find out based on that whether there is a possibility of a compound. If all clusters have the same enthalpy, then you assume that there is no possibility of a compound formation in this particular system. So, find out various possibility of clusters and compute what would be the based on the electronic configuration and based on the atomic sizes. You see one can calculate that kind of a thing and then find out which cluster has the lowest, and from that one can find out what are the possible compounds. And in some systems there are in fact more number of compounds. If you take for example aluminum nickel phase diagram, you have Al3Ni, you have AlNi, you have Ni3Al and a number of other compounds too. So, that means at specific positions you suddenly start getting intermetallic compounds. That means those clusters at that particular composition have the lowest free energy or the lowest highest bond energy, and as a result that cluster becomes stable there. And at that composition, if for example if I take an isomorphous system and if I choose all these possible combinations of 3:1, 1:1, 1:2, 1:3 and things like that, and try to calculate for each composition what is the value of this interaction, you would find that in an isomorphous system they are all equal at all compositions. That means such compounds cannot form in such a phase diagram. So, people do all these calculations and from that find out what is the possibility, and once you know that that is possible, you treat it as a phase and then start calculating the free energy for that phase too, and then incorporate it into the phase diagram and then check it experimentally whether you are able to see such a compound or not in the experimental verification. So, that is how people have been, all the CalFAD calculations are based on this. In addition, CalFAD people also have gone a little further, because these are also to some extent simpler. In some cases none of them fit. So, that is why sometimes CalFAD calculations are more kind of fitting parameters. So, instead of just one parameter which is in regular, 2 parameters in subregular, people are nowadays using in 4, 5 parameters. Basically take some experimental data that is already available, fit it with a certain model, whatever number of parameters, it is like curve fitting for you, and once you fit it, try to extrapolate that into the other parts of the phase diagram where you do not have experimental data available or it is difficult for you to do experiments. I gave you an example of copper tungsten for example. I said you simply do experiments on the copper side and tungsten side you extrapolate it, and so whatever free energy function that fits that particular experimental region, you try to find out that function and try to see, again a bit of an assumption here that I can linearly extrapolate or some other extrapolation method I can use to see that on the other side also the same thing can be used. Otherwise there is no clue for us to be able to calculate the phase diagram, because you have to start with some assumption, and people have done that kind of things as people went on calculating phase diagrams. We will have a special lecture on how to calculate phase diagrams as we go along. Now, this is all various models for finding out the free energy. After finding out the free energy, you would see, depending on the value of delta H mixing, whether it is positive or negative, the free energy curve is going to look different. For example, this is something that we have drawn for an ideal solution where the omega is 0, and if that is the case, these two parameters are g of A and g of B. I need to here tell you what would happen if I am talking about a material or a system where both A and B do not have the same structure. For example, take an example of magnesium silicon itself. If I am talking of a magnesium silicon system, magnesium, anybody knows what is the crystal structure? It is HCP. Silicon, yes, it is diamond cubic DC. Now, because these two are different, when I am talking about solid solution, for example, I want to do thermodynamics of this system. So, I am drawing a free energy curve now. What is this free energy curve for? It should be, if in this particular phase diagram, what are all the possible phases? One is there is a possibility of magnesium based solid solution where silicon dissolves into magnesium. Second, there is a possibility of silicon based solid solution where magnesium dissolves into silicon. So, I can call it as alpha magnesium or alpha silicon, whatever it is, solid solutions, two solid solutions, and there is a possibility of a liquid, there is a possibility of a compound. So, 4 phases possible in that system at various temperatures. Now, if I want to calculate the free energy of alpha magnesium and say that this curve belongs to that, the problem that I have is because of this parameter XAGA plus XBGB, this Ga is that of magnesium, Gb is that of silicon, but magnesium is HCP, silicon is diamond cubic. How do I put the free energy of both two different crystal structures into one equation and talk about free energy of alpha magnesium? So, whenever I am talking of free energy of an alpha magnesium, that is free energy of a particular structure, whenever we talk of any phase, we are talking of free energy of that structure as a function of composition and temperature. If that is the case, I need to have both these in the same structure. If Ga and Gb are two different crystal structures, then I cannot put it into that equation. That means what I need to do is I need to find out what is the stable state in this particular system. For example, magnesium stable state is HCP. So, I call this as Ga alpha. That means this is I am calculating for HCP and this is HCP. Now, but I know Gb, which is silicon, this is magnesium. Silicon is not HCP structure, but for the equation of free energy, in order to get the free energy of alpha magnesium, I need to have silicon also free energy of pure silicon in the HCP form. That is where I told you, if you go to CalFAT book by Kaufman, the first chapter is dedicated for this, on what is called lattice stability. So, people tried to calculate what would be the free energy of silicon if at all it exists as HCP, what would be the free energy of silicon if at all it exists as FCC, and that delta G. So, there he gives actually delta G of for different metals FCC to HCP, similarly delta G of silicon from diamond cubic to FCC, and so on and so forth. Once these values are calculated from first principles, I simply add this value to the actual free energy of the diamond cubic silicon. Free energy, what I can calculate from the Cp is the free energy of diamond cubic silicon only. I cannot calculate free energy of anything else from the Cp, because Cp is that of the diamond cubic silicon. What I am doing calorimetry and finding out the heat capacity is for a stable state. I cannot find out the heat capacity for something which is a metastable, which does not exist. If I put this sample into a calorimeter and measure the Cp of it, I would get the Cp of that particular structure, what it is stable at those temperatures. If I put silicon into the DSC and measure the heat capacity, I would get the heat capacity of only the diamond cubic. So, from that if I calculate H and S and get G, and that G would be only that of diamond cubic, I would not get free energy of anything else there. So, that is where I need to use these things and add them to the actual free energy of silicon that I have calculated and get the free energy of HCP silicon and put that into this equation, then only I can go forward. So, you can see free energy calculations are not, they look very simple when you draw them, this curve, but to get this curve it is not easy. So, this is how we go ahead, and that is the reason why you need to know these lattice stability criterions, and for various metals people have done this kind of calculations, and some methods are available to be able to do that. So, now if that is the case and try to draw that particular free energy, and if then after taking care of the first part, then I have to go to the second part. In the second part, if it is a non-ideal solution, then I have to add this term, and then if this term is negative, what should happen to the free energy curve. So, if you look at this, if you look at the T into delta S term, this is how T into delta S mixing term minus T into delta S mixing term, and now you have the free energy, pure metal free energy, some values whatever it is, and then in such a case, if I know that this is 0, then my free energy curve exactly becomes that of this. But if it is non-zero and if it is negative, let us assume that this. Interestingly, regular solution model, the delta H mixing is again symmetric, similar to that of delta S mixing. You can see it is omega xa xb, and that function, by looking at that function, we can say it is symmetric. It reaches either a maximum or a minimum depending on whether omega is positive or negative at 50-50. If I take xa as 0.1 and xb as 0.9, 0.1 into 0.9 is how much? 0.09, and if I take it as 0.5, then it is 0.25. So, 0.25 is the highest. So, wherever composition I take, I will see that the maximum of xa xb is at 50-50. So, as a result, if the omega is negative, then this will have a symmetric curve, and if this is a symmetric curve, my free energy function would be this is delta H and this is G of alpha, G of alpha. I add these two, and only one small thing that I have done is I have drawn it from here. If in principle I should call this as delta G mixing, this is actually delta G mixing. Addition of these two gives me delta G mixing, because this is 0, this is 0, and this delta G mixing, if I add it to my pure metal components, if my pure metal components have free energy values of these two, this is Ga, this is Gb, then I would know that my value would be something like this. Something like this. This is the actual G of alpha, because this delta G mixing has to be added to the pure metal component, which is the first part of the equation, then I will get the G. Now, when I am talking of this G, depending on whether the omega is positive or negative, as long as omega is negative, your free energy curve will always be plunging downwards. The moment omega is positive, then you would see that there is a possibility of situation. Let us say take a particular case, again I will reuse this itself. So, I say that entropy of mixing is not changing, obviously it will not change, is not it? Any system that I choose, entropy of mixing is the same. We said before that this part is unbiased by what element it is, because there is no element coming in there, it is simply composition. So, that is why whether I take nickel aluminum system or magnesium silicon system, it will have the same configurational entropy whenever I take a 50-50 composition. It does not depend on whether it is nickel aluminum or magnesium silicon. What comes in terms of what is the system, it is here. The system is represented only in omega, and of course here the actual pure metal values. So, the interaction between two elements comes only in this, and if that is positive, if it is following a regular solution model and if it is positive, then what should happen to the free energy curve? This is delta H mixing now, and this is T into delta S mixing minus T into delta S mixing. Combination of these two would give me delta G mixing. Now, depending on how much is this with respect to this, you are going to see the effect. If T into delta S mixing is larger than delta H mixing, this delta G mixing will be still negative, and accordingly you would see that this value would cause something like this, the actual G would turn out to be something like this. This is the delta G mixing, and if you add the delta G mixing to two pure metal, you would get a actual free energy curve. G alpha will be like this. But now if you see that this is going to be larger than this value, then you would end up in situations where the actual free energy curve may be something like this. And you may ask me why it should go down and then come up. Why can't we have a free energy curve which goes like this? That is where the question that Anisha has asked in one of the last classes comes into picture. Now if you take this particular equation, which is XA plus XB plus omega XA plus RT XA ln XA plus XB ln XB, and try to find out the slope of it, that means differentiate this equation with respect to XB, knowing pretty well that XA plus XB equal to 1, and try to differentiate this and find out that value of dou G by dou X B at XA equal to 1 or XB equal to 1. I want to give this as an exercise to you. Please do it in your rooms and come back to me in the next class. You would see that if you do this, you would find this value is minus infinity. Please do it for yourself. So the slope of free energy versus composition Gx diagram, the slope of the free energy curve as the XA tends to 1 or XB tends to 1 is minus infinity. That means free energy always has to go down. That means free energy has to, that means when I add a small amount of B to A, free energy decreases, because this is the function, and this for this function this is what you get. And if you get that, then you see when you add a small amount of B to A or small amount of A to B, you would see that free energy can never increase. Later as you add more and more B to A, it may start increasing because of this being positive, but towards the two pure metal ends, this however positive omega is, because of the nature of this ln XA, and differential of ln XA brings you that. You would see as we go along, as if you calculate that, if you do this differentiation, you would see that you would tend to see that whatever may be the value of omega, however repulsive the interaction between the two metal C's, but on the two pure metal ends the free energy has to decrease when you add the two, and that is the reason why you see it is very difficult to purify a metal. You can talk about 4 nines, 5 nines, 6 nines, but you can never talk about 100% of A or 100% of B. And the more nines you want, the more difficult it is, because you are somehow pulling the system away from its nature. It wants to have the elements inside it, and such metals are not really stable also. Any possibility they would try to grab a little bit of oxygen from the atmosphere or something like that. So that is why you would see one can calculate this and then see. Okay, this is one aspect. Now the second aspect that is important for us to know, and we will come back to this when we are talking about phase diagrams. Second aspect is, whenever I have a free energy curve for like this, there is one parameter which we define called chemical potential. All of you must have come across this. How do you define a chemical potential?
Change the free energy of the whole system by the small addition of the.
Correct. change in free energy as a function of composition. Basically, if you want to relate this, if I draw, if you take this particular curve and draw at any particular composition a tangent to the free energy curve, wherever this intersects, these two values give me on one side chemical potential of A in alpha, if this is a alpha phase, this is chemical potential of B in alpha. Chemical potential indicates what is called the activity, because there is a relation between chemical potential and activity. You must have seen RT ln A, that equation you must have seen. So, chemical potential is always proportional to the activity, or activity is proportional to the chemical. So, whenever you see a chemical potential of for a particular element in a phase is higher, we say that particular element is more active in that particular phase. Here, for example, if I draw this and I show you that mu B in alpha is higher than mu A in alpha, I can say that for that composition at that temperature, B atoms are more active in alpha than A atoms. So, activity and chemical potential are directly related, and this is what we are going to use it to understand what is called the equilibrium between two phases. When you bring two phases together and keep them together, what would happen? So, at any composition, and these chemical potentials are not fixed for a given temperature, they depend on the composition. For example, the same phase, I come to here on this side of the free energy diagram and again draw a tangent. You would see that this is mu B in alpha, this is mu A in alpha. That means these two compositions, if I take alpha of let us say 30% B and alpha of 70% B and take two of those pieces of these two alpha, you would see the alpha on this side would have higher activity for pure A when compared to B, and on this side higher activity for pure B. So, in principle, if I bring these two pieces of let us say two alphas, let us say one has 30% of zinc whatever it is B element, and one has 70% of B element, bring them, weld them together, hold it at that particular temperature as a function of time, you would see, because one has B atoms being more active, another has A atoms being more active, you would see from this side B atoms will diffuse towards this side, A atoms will diffuse from this to this, and both of them will come to an equilibrium at some stage, so that the composition of both the mixtures will become same of some equilibrium composition. If I take the same phase, if I now take two phases with two different compositions, what would happen? You would see that in a minute. For example, if I take two phases, I can always represent two phases with two free energy curves. The only deliberately I am drawing these points different, because I do not know. And carefully, if you observe now, let us take a system of let us say aluminum silicon or magnesium silicon again. If you draw these two free energy curves, one is for that of alpha magnesium, let us say, another is for alpha silicon, you will see on the pure magnesium side and pure silicon side, you would see 2 points here and 2 points here. What does those 2 points mean? On the two pure metal ends, you have two free energy points. What are those two free energy points? Yeah, these 2 points, can you tell me first? What are these 2 points? And what is the second one? I am talking of this side, do not again bring. Yes, this is the free energy of magnesium in the alpha form, this is the free energy of magnesium in the diamond cubic form or HCP. When I say alpha, this is magnesium, G of magnesium in the HCP form, and this is G of magnesium in the diamond cubic form. And obviously, the free energy of magnesium in the diamond cubic form has to be higher. And similarly, on this side, if I see that this is free energy of silicon in the diamond cubic form, and this is free energy of silicon in the HCP form. And if I carefully observe, for one particular curve, I am using free energy of the same structures, pure metals, for calculating that free energy. If I take this particular curve, I am using HCP, HCP. If I am using this curve, I am using diamond cubic, diamond cubic. Otherwise, you cannot draw the free energy curve. So, this is how free energy of two different phases, if I assume these are the two at room temperature, in principle, let us say I am forgetting the existence of intermetallic. Now, if you want even to bring in intermetallic into the picture, you can also draw that, but for today's class we do not need it. In the next class we will bring that. Now, if I look at two compositions of magnesium magnesium silicon alloys, one let us say containing about 20% silicon, one piece containing 20% of silicon in magnesium, another piece containing let us say 80% of silicon magnesium, and then put them. Let us say this is one composition, this is one another composition somewhere here. If I draw the free energy curves and draw the tangents, so that means basically what I am doing is I am taking two pieces of alloys, welding them together, one containing 20% silicon, another containing 80% silicon, weld them together, hold them at that temperature and see what happens. You would see actually that whenever I do this, there is, because the activities are different, and which is represented by these free energy curves and the tangents to them. For example, if I draw a tangent at this particular composition, I will see that this tangent goes like this, and similarly if I draw a tangent, this tangent goes like this. And now if I look at it, what are these values? This is mu of magnesium in alpha magnesium. This is mu, I am sorry, I will, this is mu of magnesium in alpha silicon. This is the alpha silicon solid solution. So, that where it is intersecting. Similarly, this intersection is mu of silicon in alpha magnesium. This is mu of silicon in alpha silicon. This side is pure silicon side, this side is pure magnesium side. So, the two chemical potential, always remember, we cannot say this is the chemical potential of a particular phase, we always say this is the chemical potential of a particular element. Chemical potential is always for a given element, activity is always for a given element, activity is never for a phase, activity of elements we talk about. Similarly, chemical potentials of elements, element in which phase, that is what we look at. So, if you look at it, this is chemical potential of magnesium in the alpha silicon, this is the chemical potential of magnesium in alpha magnesium. What does this tell you? This tells me that the chemical potential of magnesium in alpha magnesium is higher than the chemical potential of magnesium in alpha silicon. So, in my mixture, in my piece that I have taken, two pieces that I have taken, one is that this is alpha magnesium side, this is alpha silicon side, 20% magnesium, 80% silicon I said. One is the alpha silicon side, another is alpha magnesium side. On the alpha magnesium side, if I look at it, the activity of magnesium is high, and if you look at it alpha magnesium side, alpha activity of silicon is lower. So, this here you have higher activity of magnesium, lower activity of silicon. Here you have higher activity of silicon, lower activity of magnesium. As a result, you see that the silicon atoms will diffuse this direction, magnesium atoms will diffuse in this direction, because you have a higher activity there. So, if I look at for a given element, because the activity in the alpha magnesium is higher, so this element moves from alpha magnesium side to alpha silicon side. Similarly, silicon moves from alpha silicon side to alpha magnesium side, and in the process what happens? In the process, the composition of the two start changing. Alpha magnesium would keep on getting more and more silicon, and alpha silicon would start getting more and more magnesium. So, these two compositions will start moving towards each other. When more magnesium is added to alpha silicon, the composition will move this direction. When more silicon is added to alpha magnesium, the composition will move towards this direction. So, the alloy composition of the two phases starts moving from here to here and from here to here, something like that. And now, at these two different new compositions, if I again draw the common tangents, if I draw the tangents, I will see that these tangents now will start moving. In fact, if you take slightly off, I will show you that these tangents would start moving like this. If the composition changes from here to here, here to here, this is the first case. This is the first case. From there you have come to case number 2. From 1 to 2, if you have moved, you see what has happened is this difference has come down. What does it mean? That means the activities of the two pure metals in the two phases are coming closer, and as this keeps on happening, at some stage you would see that you reach a particular composition of alpha magnesium and a particular composition of alpha silicon, such that when I draw a tangent for one, that tangent becomes this tangent also for the other phase. This is what we call it as a common tangent. So, that means you would reach a situation where the tangents are the same. When the tangents are the same, what does it mean? This particular composition is mu magnesium, mu of magnesium in alpha magnesium. It is also mu of magnesium in alpha silicon. Activity of magnesium in alpha magnesium and activity of magnesium in alpha silicon becomes the same, and once the activity on both the sides is the same, then the atoms cannot move, and that is the definition of equilibrium. In any multi component system, equilibrium is defined not simply by which has a lower free energy, it is defined by equality of chemical potentials, and when the chemical potentials become equal, then one element cannot move from the other from one side to the other. Then you see wherever the elements are, they remain there, and that is an equilibrium, thermal equilibrium. At that temperature, and within that material there may be thermal vibrations, because the temperature is not absolute 0. Thermal vibrations are there in alpha magnesium also, thermal vibrations are there in alpha silicon also. Atoms are moving in that, but they are not moving in across the interface, and because there is no activity gradient, the gradient in the activity has become 0. And once that is the reason why whenever you remember long back, if you remember Fick's first law, J equal to minus d dc by dx. All of you in one voice you have said dc by dx, actually it is not dc by dx. You would see this difference if you have seen taken any ternary system. For example, if you take, people have done this interesting experiment, they have taken a cast iron with about 3% carbon in it, but about 2% of silicon in it. This cast iron, they welded it to another steel containing about 0.4% carbon. What do you expect when these two are kept at high temperature? You expect that the carbon should diffuse from the cast iron side to the steel side, isn't it? One side is 3% carbon, another side is 0.4% carbon. You actually see the reverse. Carbon will go from the steel side to the cast iron side. People started calling this as uphill diffusion, and the reason is here is, though the concentration gradient is there, there is no chemical potential gradient. The reason is silicon, the moment it is present, it locks up the carbon and reduces the activity of carbon atoms. There are certain elements which have this tendency. For example, compound forming elements, carbide forming elements, the moment I add to an alloy steel, all these carbide forming elements will lock up the carbon. Let us say I add chromium, vanadium, titanium to a cast iron or a steel, you see that all these lock up the carbon and reduce the activity of carbon. Once the carbon forms a compound, the carbon atoms cannot move further because they are strongly bonded with some other element. So, once this activity of carbon comes down, now you have to actually see the activity gradient and not the concentration gradient, and people have actually done this, and this problem does not arise if I am taking two binary systems. Let us say one steel of 0.4% carbon, another steel of 1% carbon with no other alloying elements present in it. If I take, definitely from carbon will flow from 1% carbon side to 0.4% carbon side, there is no problem. So, because there the chemical potential is driven by the concentration gradient, chemical potential is whereas in a ternary cases the chemical potentials are changed because of the presence of ternary interactions, and that is what we have to remember, and that is how we understand the chemical potential. So, we should say that it is mu of A in alpha should be equal to mu of A in beta as the equilibrium concept. Okay? With this we will stop.